Okay, so this is question number 4, and we are going to talk about continuous random variables once again. And we have a joint probability density function of x and y at the same time. And this joint probability density function is equal to 12 over 5x times 2 minus x minus y in parentheses. So this time we have something a little complicated, okay, a little salty. And the random variables x and y here, they are taking values in the unit interval, both of them. So again, the boundaries of these joint distributions is simple. Now, in part A, it asks me what is the conditional probability density function of x given that y is equal to y. So here it says y is observed and observed to be equal to a variable y, an arbitrary variable. So it makes me calculate the conditional PDF of x for an observation of y, which is equal to y. Now, for example, then if it asks me to answer this question in part C to calculate the probability of the conditional probability of x being between 0.2 and 0.8, given that y is equal to 0.5, then what I am going to do is, once I determine that conditional PDF of x, given that y observed to be a general variable y, I will just plug in 0.5 in place of that y first. So that conditional PDF is going to be conditional on the observation of y being equal to 0.5. So then I'm going to answer part C. So step by step, it basically asks me to compute the conditional PDF of x for an arbitrary observation of y, which is basically lowercase y, any value of them. It does not necessarily need to give me a specific observation. Okay, it says that it is observed to be equal to y. So let's compute it. But you know, in order to compute the conditional PDF of x given y, we need to divide the joint PDF of x and y to the marginal PDF of the conditioned random variable, which is y. Now, first we need to compute the marginal PDF of y here. Okay, so what is the marginal PDF of y? We are supposed to integrate the joint PDF over the x variable, over the x operator throughout the whole domain of x, and x is taking values between 0 and 1 at anywhere, and we need to integrate that function, and that function is integrated with respect to x as 24x minus 12x squared minus 12xy over 5. Now we need to plug in 1 and 0 values in place of x after the integral, and that is going to summarize the function as 8 minus 6y over 5. So 8 minus 6y over 5 is going to be the marginal probability density function of y. Now, of course, we have not answered the question yet. Please be careful. And the conditional PDF of x, given that y is observed to be equal to y, is what? The joint probability density function divided by the marginal PDF of y at y. Okay, so because it says y is observed to be equal to any general value y, we are not going to plug anything in place of y yet. Okay, we are going to leave it to the second part of the question. So when you divide the joint PDF to this marginal PDF of y, you are going to get a function which is a function of x originally, but it also seems like a function of y as well, because we do not exactly specifically know the observation, right? So we observed y to be equal to y, but there is no specification here. So because we do not have a specification, this function is actually a function of x. It is a conditional PDF of x, but because y is not specified yet, it also seems as if it is a function of y as well. Okay, so but it is not. This function is a PDF of x, not PDF of y. When y is specifically determined, for example here, y in the function that we are observing here. And when you plug in 0.5 in place of y, you are going to get 18x minus 12x squared over 5. So that is the conditional PDF of x, given that we observe y to be specifically equal to 0.5. Okay? And finally, for part C, it asks us to calculate the probability, conditional probability of x to be between 0.2 and 0.8, given that y is equal to 0.5. And in order to calculate such probability, such conditional probability, which is defined as an interval for a continuous random variable, we need to integrate its conditional probability density function from 0.2 to 0.8, but specifically conditioned on the observation of y to be equal to 0.5, which is exactly that function we see in B. And after the integral of the conditional PDF, we get 0.6768 as a result. Now, I'm not going to explain the details of the integrals anymore. I mean, you should be at this point, after weeks of classes where we integrate polynomials and exponential functions, I think you should be professional in calculating such integrals, I guess. So it is your job, not mine. Therefore, all I am showing is the direction. I am showing the way.